So today we're with Gerardo Gonzalez, who's our mechanical engineering manager. And one of the things that Gerardo's team is developing is our cutting system. So we're going to kind of talk through some of the key features of the cutting system with Gerardo, see what we're doing, some of the innovations that we're driving with that. So and talk through some of the key features of the design with us.
Sure. Thank you, Ben. So this is the end effector, basically the cutting system of the Monogram TKA system. And so I would like to start talking a little bit about the cutting tool and some of the features, some of the thoughts behind the design. It's a helical flute type of cutting tool. The helix has around 30 degrees of angle. It's capable of doing in milling cutting and side cutting. It's powered by a 150 watts motor that's inside this main body of the end effector. It's pretty powerful for the job that is meant to do. It's capable to go from anything between 15 and 40,000 RPMs. We're planning to do a lot of testing within that range. It's of course made out of biocompatible material, and kind of the strategy behind the way we're machining the bone compared to how a typical sagittal saw does it. So basically the sagittal saw moves in this direction very rapidly, and it's basically cutting with a length of approximately 20 millimeters, and our rotating cutting tool has a 6 millimeter diameter, but it's significantly longer. So the length of the flute is 30 millimeters, which you can see the difference. So while it is true that a rotating cutting tool needs to obliterate more material, we have the freedom to select how deep we side cut. So we can go as deep as the diameter of the tool, and even deeper, like undercutting. And we can, in one pass, we can cut up to 30 millimeters. I mean, the total length of the flute. So in comparison, we could remove the same amount of material on every pass, if not more, depending on the conditions. Exactly. And the limitation of temperature.
So at a high level, Gerardo, so the key idea is some of the most prominent robotic systems have sagittal cutting as part of a feature. Mm-hmm. Our tool is rotary cutting.
Yes.
And our goal is to optimize speed. And we believe that we can do that with a rotary tool because of how we've designed the rotary tool. Is that right?
Exactly, yeah. We're planning to do a lot of testing with the rotating cutting tool. And the main goal of the cutting system is of course being as fast and effective, as efficient as a sagittal saw system is.
Exactly. So one of the key things, if you just think about every CNC in the world, right, is pretty much a rotary cutting tool. We don't know of anything in the market today that actually sort of reproduces effectively a CNC end mill, and that's what we're doing. So we believe we can get really super efficient cutting. What are some of the other features that you've designed in, Gerardo? Kind of walk us through. I see that there's looks like irrigation tubing.
Yes, this silicone line, it's exactly what it is. It's an irrigation line that will provide an adjustable flow of sterile fluid to control the temperature of the material being cut, of the bone.
Why don't you show us how that snaps on?
Well, this is basically adjustable depending on the setup, specific setups, depending if it's going to be a left knee or a right knee. The approach angle of the arm will change, and these can be quickly adjusted depending on the most convenient orientation of the line to use gravity to fed the fluid through the tool and until the cutting plane. And yeah, It's removable, but it keeps in place in the desired angle, the desired
Terrific.
orientation. And the control of the flow, it's on the screen, so the surgeon or whoever is assisting the surgeon would have
Variable
control of
flow
that.
rate.
Variable flow rate, yeah.
What are these 4 gray dots there? that I
Those
see?
are fiducial markers. So basically what they are optical markers that are visible for the camera. That's the camera that we're using is basically, I would say like, they are the equivalent of the eyes of the robot. So
Yes.
the robot sees and understands where critical things in the system are in space. So these fiducial markers are made of a reflective material that they basically shine with infrared light that's been sent by the
Yeah.
by the camera, right?
So one of the questions we get, right, is, are robotics safe, and what safety features does the robot have? So one of the layers of safety we have, right, is we are tracking very accurately the position of the end effector at all times. And maybe Gerardo, you can talk about how precise we know exactly where the tip is. I mean, maybe talk through the tolerances of your design and why everything is so critically well designed.
Yeah, sure. Well, first of all, like I mentioned, the fiducials, this particular array of fiducials that are visible to the camera, they let the robot know the exact position of the end effector, and then the transform between the end effector and the tip of the tool, it's a constant, and the positional accuracy of the cutting tool is critical. So the mechanicals, the internals in the collet mechanism and in the motor shaft, everything is considering that. All the bearings in the system are preloaded, so there's no axial play. So once the cutting tool approaches the bone, there's no movement of the tool to maximize the true position accuracy of the cutting tool.
Maybe you could show us like the spin the bear, just to show us kind of give us a sense of how true that spins.
Yeah. So this is a different cutting tool, but it's basically the same collet mechanism that's installed in the end effector right now. So on the back of these cutting tools is the same type of feature that engages into the collet mechanism, and then this rotating movement compresses a little collet inside to grab on the tool, and now the collet is engaged to the cutting tool. So those bearings that are allowing this movement are the ones that will allow the tool to rotate at a very high speed. Of course, in reality, this end of the assembly it's not moving, but it's the cutting tool, the one moving.
With almost
very,
no
very fast.
axial play. So again, everything
Yes.
we're doing is about accurately cutting.
As is mechanically possible. Yeah.
With that, it's safety features of knowing where everything is with cameras. And maybe you could talk about the bearings that you've spec'd into those.
Well, they're ultra high speed bearings. They're sealed. They're pre-lubed. They are designed with very, very high tolerances. The dimension of the inner race and the outer race, they can only vary in 2/10,000ths of an inch. So we're taking advantage of that with the components that surround the bearings to provide the system with the best mechanical accuracy that's possible. And we can see that. I mean, one simple experiment that we can do is just put a little bit of a spin here and then see how it behaves with different loads. Like right now I'm putting a radial loader, I'm changing the angle. Now I'm putting axial load on them, and the system is pretty.
So basically,
pretty
we've
smooth.
spec'd out, a CNC router bearings. I mean, it's the accuracy of a CNC router.
I would say it's a little higher than that.
Higher
Yeah,
than that,
it's
yeah.
It's higher than just the mechanical mill spindle assembly.
Okay. And how does the end effector attach and detach from the robot arm?
We're using a quick connector. It's pretty simple to use. There's actually a button on the top of the flange that
So
releases
just,
the system and keeps it in place for safety. So it's a little bit redundant, and now it can be taken off. So it's basically a quick changer.
Quick release.
For a quick release system to not only provide a very quick removal of the tool, but can also be interchanged if for any reason a different end effector needs to be used. As far as it has the mating part, it's very simple and very quick to be changed. And it's probably worth mentioning that it's a kinetic joint.
Mm-hmm.
So the repetibility of the true position of everything that is attached to it, it's very high. It's 0.02 millimeters of
Okay. Incredible
repetibility.
accuracy. Probably worth also saying every single end effector is going to be calibrated, basically measured, and that data will be stored, right?
Yes, we're planning to do that in the near future. Every single end effector, of course, there's always will be minuscule variations in the system, so we're planning to measure those variations and store them in a digital file that could be stored in the end effector itself, or we could probably etch a QR code on some of the surfaces so that it can be scanned at any time, and no one in the operating room needs to worry about where mini card is located, or to download it from the web, because the Wi-Fi could be compromised at some point in time. So it could be just scanned from the surface of the end effector.
And I know heat was another consideration. So we've been concerned with heat. Talk a little bit about heat dissipation and making sure that it's safe to touch and that kind of thing.
Yeah, you're totally right. The life of the motor depends greatly on how well the heat that it generates is dissipated.
Mm-hmm.
So the plan here is to keep a significant amount of mass around the motor. This is a solid piece of heat-treated aluminum. It's a specific aluminum alloy, and we've calculated that with this amount of mass and being in direct contact with the motor, it'll dissipate more than 90% of the heat that's generated from the motor, and it'll keep it healthy for many hours.
It can run continuous runtime is really the key, right? We don't want to have these motors failing.
Yes, yeah. The heat is not a limitation for keeping the motor running continuously. We can turn on this motor and let it run until it dies after thousands of hours.
And every case would have a backup end effector as well. So talk a little bit about cleaning and sterilization and some of the considerations you had to.
Sure. Yeah. The entire end effector is designed to be it's completely sealed. So even if the motor it's rated to be autoclavable, we're sealing all the points of entry to access the motor. So it'll be completely safe to include hand wash or washing it on the running water as part of the reprocessing after every case, and then after it's pre-clean or pre-washed, it can be autoclaved or autoclaved in any standard autoclaving machine in a standard cycle of 15 psi and 135 Celsius degree. It's pretty safe. The motor itself is rated and tested for 1,000 cycles, and with the extra protection that we are providing with the design, we can autoclave this end effector more than 1,000 times.
Wow, terrific. And I see that our founder just walked
I'm
in.
not on this one.
Well, maybe you could say, what do you like about the design? Maybe come talk about the cutting system a little bit.
Actually, I have a question, Gerard. So we were talking yesterday about cutting aluminum out. But listening to you, I mean, that's the heat sink for the motor, correct? So it sounds like we're not going to be able to cut. Like if we cut out all this mass from here,
We could, I mean, there's a fine trade-off between the amount of mass and the amount of surface that dissipates the heat. The mass kind of absorbs the heat, but the area expels the heat to the environment. So
Okay.
we could find the sweet spot, and maybe we could add some recesses here that would reduce the mass, but would increase the exposed area of the material.
Okay.
And then we can find the point to maximize that.
Yeah, so I mean, right now, just to kind of summarize that, you know, everything is a balance, right? So the mass of the end effector can affect a very small level the accuracy of the robot, right? The more mass the robot has to carry, potentially it could impact the accuracy of the cutting.
That's
So-
a good point. Yeah. Fortunately, the KUKA arm that we have selected has very high quality brakes and very positional accuracy.
Mhm.
So in the total payload of the arm is in the range of 30 pounds, and the total weight of the end effector is in the range of 7 pounds.
Mhm.
So it's not even close to the limit of the payload. So even if we're not planning to move the end effector rapidly in space, the robot is capable to handle this weight, this load with a big safety factor.
I see you have some sawbones in the back there. Maybe you could grab that femur or the tibia,
Sure.
just to sort of show, give the audience a sense for how the cuts are going to be actually executed.
Yeah.
How many passes, for example, are we going to need to resect the tibia?
To resect the tibia, well, for example, this is an example of a tibia that's been already resected. Of course, this is a polyurethane foam bone that we use for our testing. So basically, the approach angle for doing the proximal tibia cut here would be something similar to this, having the patient laying on the bed and having the knee flexed in 45 degrees. I'm going to move the bone, but in reality, the bone is still and the end effector is moving. So the cutting tool would approach the cut in this direction, and then it will go as deep as the pre-operative plan and the cutting tool path dictates, and then it'll move laterally or medially, depending on the direction. And a cut like this should be able to be done in 4 passes or maybe less.
Yeah. Again, so what we're competing against, just to really summarize, right, is the current state of the art is to cut this.
Yeah,
With a saw.
exactly. The way that it would be cut with a sagittal saw would be, of course, placing the guide blocks prior to the cut, and then using them as reference, and then cut in this direction, and moving along the plane all the way to the back,
Yeah.
and
So terrific.